now let's look at the second category of HFSS designs that we'll have to deal with, which is the 3D structures. Now, unlike the 2D structures, they don't have a similar flow, but I feel they're easier than the 2D structures. We'll have a look at them. There are two of them that we'll have to deal with. The first one is Rectangular Waveguide, which is the first one I'll be explaining, and the second one is Magic T. Honestly, if you get Magic T, it is the easiest thing to do. There is very few steps required in that in total. That's the easiest thing, and Rectangular Waveguide is slightly more complex than that. Not an issue. We'll look at all of the steps. Before we jump into designing a rectangular waveguide, let us look at a completed design first so that we know what we're dealing with. So here we have a completed rectangular waveguide structure, and let's see what exactly we're looking at. This is technically just a metal tube, a hollow metal tube actually. So if we just zoom in here, you can see there's a thickness to this metal. So, and there's just this thickness and inside it's hollow. To be more precise, there's air inside of this. So we'll have to construct it just like this. So the way to do this is quite simple. We'll just be creating one box, an outer box, and then subtracting an inner box from it. And that's how you will get the hollow tube. Another important thing to note here is the radiation box, which is actually slightly different than what we have observed before. We can see here that the padding at these two, entry and the exit of the waveguides, have been reduced to 0, as opposed to other structures where there is all padding in all directions. The reason for doing this is the type of port that we have chosen, which is actually a wave port. So over here under the excitations tab, you can see here, and there's a different kind of port. This is not a model lumped port. This is a wave port. I will be explaining how that is different and how I can place it in the Ansys tool later. But this is what we have placed here for excitation, and this is also the reason the radiation boundary has been set to 0 padding at the entry and the exit. By padding, I just simply mean the distance from the structure till the radiation box. You can see that on top here there is this distance from the structure to the radiation box that is non-existent on the sides, on the entry and the exit. Now let us get started with actually designing this. So I'll close it. I can just do HFSS as, so I'll close it. And in new structure, I can just do HFSS. In the new structure, we'll do HFSS here. This is the same way we start up all files that we've seen before. And now that we're at the blank canvas, let us start creating this design. So the first thing we'll have to do is create a first outer box. Does not matter how it looks, it can be arbitrary. And now we'll look into how we will actually change the dimensions of this in our favor. So we'll go to create box here on the left. And now we'll look at the geometry, which is quite similar to what we've done before. Let's first start by placing this position at 0, 0, 0, and then also changing the size. Now for the rectangular waveguide, out of the total 6 experiments, 3 of them are rectangular waveguide, and in each of them they've given 2 of these 3 dimensions, so it makes life a lot easier actually. I'll be taking the 10 gigahertz case where they've given the values 22.86 and 10.16. These are the values that they've given in the question, and this Z size will be a constant 60 millimeters irrespective of the question. So if they've given you different values, then these two values will change, but this Z size will remain 60. Click apply, and as we see, okay, there is a slight distortion with the design, and there's a very easy way to fix this. This is an error that can show up in during the exam as well. So I'll go over this. All I have to do is just save the design, save it anywhere. Okay, just save it here, and then close Ansys and then open the file again. So we can go into files and open the file again. mind, I'll be restarting that. And then open I can just do HFSS as so. I'll close it, and in a new structure I can just do HFSS. In the new structure I'll do HFSS here. This is the same way that we open a blank canvas in every project that we have done before, and it will continue this as well. Now that we are on the blank canvas, now let's look at the actual design of it. And like I mentioned earlier, it's simply we'll start with a blank box. Doesn't matter about the dimensions, that is absolutely irrelevant right now. We will be changing it as per our convenience. That we can go into create box and do so, and removing it here, and then we can change what we require. So like we did before, we'll be changing the coordinate system first to 0, 0, 0 to see which is the point that is actually being affected. So you can see it is this point here, the bottom left point, that is what we'll have to change. Now when it comes to size, out of the 6 experiments that they've given in the lab, 3 of them are rectangular waveguide, and in each of them they're given a different dimension for the required frequency, and those are 2 of the 3 dimensions that we have to give here. So I'll be taking, for example, the 10 gigahertz case where they've given the dimensions 22.86 and 10.16. These are dimensions that are directly given in the question, and the Z size will be 60 irrespective of which frequency it is. This is just the length, the final overall length of the waveguide. You'll have a look when we click apply. Once this happens, there is a small error with the design here. This is very easily fixable. All you have to do is save this file once. I'll just save it somewhere here, and then once it's saved, I'll just close it and then reopen it. So I can reopen it from here. Once this reopens, the structure will come back to normal. Yes, this is the structure. This is the rectangular waveguide. Now we have made the first box on the outside and with the right dimensions. What we have to do is now create a second box on the inside. Let's look at how we'll be doing that. Let's first make an arbitrary box, and let's look at how we'll be changing the dimensions. Before this, what I would suggest is making this outer box transparent so that you can see what's actually going on inside. The way you can do that is by choosing the box here. I think we've mentioned this before, that out of these 2 options, the top option is for changing things like transparency and color, whereas the bottom option, if you double click this, you will get, for example, position and dimensions. Over here you have to change the transparency, so I'll click on the name itself, and in the transparent option here, it'll allow us to set a particular transparency. Put it anything, doesn't matter. This will just allow you to see through the box. It's not a necessary step, I'm just letting you guys know. All right, let's look at this structure. Let us see how this has to be influenced. Let's start with a 0, 0, 0 as usual and apply this. Now this is the point that is getting needs to be changed. Now we're not sure if the x size and the y size here, so what, instead of mugging up the values, I would like to take a step-by-step approach so it's a bit more intuitive. What we can do is, if we compare it to the main design, there is a particular thickness that is there for the metal. That thickness is actually 0.2 millimeters. So I'm not sure how exactly I can design it here as of now. So what I will do is I will give it the same dimensions as the main big structure, 10.16 and 60. What this will do is it will give me another box that is exactly as big as this. All right, but this is not what I want. I want a box that is smaller than this. So the way I'll do that is by subtracting the thickness. Now the thickness is 0.2, but we can't only subtract the thickness. We'll actually have to subtract it twice. And the reason for that will be quite evident once I show that to you in the actual file. That file should be here. If you look at the original design, what we can note from here is the outer box has a particular dimension. So in this case, in our case, this bottom dimension is 22 and the top direction is 10. And we need another box which is 0.2 millimeter offset from all directions. So you can probably imagine, do some very basic math and see what the dimension of this box will be. So if we just look at this side, for example, this is 10.16 whatever. We have to subtract this 0.2 as well as this 0.2 so that we can get this length. This is the final length that we require. So we'll have to do 10.16, which is this length, divided by 2 times the thickness. And similarly for the length as well, this is 22.86. We have to subtract this thickness as well as this thickness. So we have to do 22.86 minus 0.2 minus 0.2. Now we can change that in our design. This is our design. Over here we can just change the size to minus 2 times 0.2. This is just the thickness. You can do minus 0.4, doesn't matter. 2 times 0.2. If you haven't looked at this before, you can do some very basic math within this Ansys as well. This will just give you the direction. This will give you the direct result. If you click apply, you can see that inside box has become smaller. But I do not think we have still got what we were looking for, because you can see that the box is actually not in the middle of this box. You can see that there is a small offset that we need to still fix. That offset is very easily fixable, because I think if you just look at this hard enough, you'll be able to understand what is actually missing. This point is where the coordinate system begins. It has to be shifted a little bit diagonally upwards and to the right so that it can fit in the middle, and that is very simple to do. If you go here, so you remember that this is the coordinate point that is being affected. So I will choose this. Yes, this is the coordinate point, and I have to move this diagonally upwards and to the right. Diagonally upwards is y. So what will happen? I'll have to move it upwards by 0.2. So upwards by 0.2, and I have to move it rightwards by 0.2. So 0.2. That's all I have to do, and I think that's quite evident why we did that. And now you can see. Okay, there seems to be still a little bit of missing here. Actually, this is not moved in the x direction. Yes, my bad. I have done a small error. So this is not 0.2, this is 0. The reason, you can see it's quite clearly visible. We have to move it upwards in the y direction and rightwards in the x direction. It's quite evidently visible here. I have to move it rightwards in the x direction. So this will be not this, it will be 0.2 here. And once that is done, you will see that what we require has been achieved. This box is directly in the center, and it's easily done by moving this coordinate point upwards and to the right. So upwards by 0.2 and rightwards by 0.2. That's all. Now what we'll have to do is, both of these are solid boxes. So we'll have to actually subtract the inside box from the outside box. And that's very easy to do, but right before we do that, I will copy this box and paste it again. So I just did Control C and Control V. So now we have two of these boxes, and the reason for doing this will be quite evident soon. I'll just leave that there. What I'll do is simply subtract box 2 from box 1. The way to do that is you select the outer box first, select the next box after that, and then there's a subtract option here. Now in Ansys 2023, this option might not be very obviously visible to you because actually the screen size is smaller there. So you will actually look at it something like this. You'll have these options like draw, operations, measure, something like that. So to go to operations, and over here you'll find subtract. So you'll have to do that. This is how it will look at in the Ansys 2023 in the lab. So you do subtract, click OK. And what that does is it subtracts the box 2 from the box 1. So now box 1 is simply just a hollow box. It's this hollow box. And the reason I duplicated this is because if this was not present, example, this wasn't present and this was actually a hollow box, there is a vacuum present inside this waveguide. And that is not what we want, because by default it will be vacuum. That's not what we want. We actually want a air inside this waveguide. And that is why this box 3 is important. This box 3 will act as the air. When we assign material in the future, we will assign box 3 as air. If we don't do that, then it will be vacuum inside, which is not what we want. So this is the rectangular waveguide done. That is all that is required for this. Now we will move on to the next further steps. The first one is to add the port. We'll have to add two ports here as usual. Waveguide port, the wave port is what we'll be adding here. So the way you add that is you have to just first draw a rectangle as we usually do. So you can see you have to draw a rectangle here on this face, on the air face. All right. So I'll just take a rectangle, and not from the outside. You have to do it from the inside. This is only where the wave port has to exist. Yes, this is the wave port. This is the for it, and I'll right click on rectangle, assign excitation port, and you have to go to model wave port here. Okay. Now once we're over here, we'll have to choose the integration line, and this is where one thing changes in comparison to the other things. Now usually what we do here is we just choose new line, but over here we also have to take care of the question that they've given. They've talked about propagating modes. They want to see the first few propagating modes of this rectangular waveguide, and the way you do that is by changing the number of modes to 4. Simple as that. And now you can just follow the same thing we did before. Integration line, new line. And the same way we've done new line before is we just have to wait for this rectangle. This rectangle will basically tell me that I am on the midpoint of this line. Rectangle, you have to go for the triangle on the top half of this where the rectangle begins, and we have to go here where the rectangle ends. Like that. Done. Now you're done with this. Same thing has to be applied on the other side. So go ahead and add the rectangle, same as usual. Then you will assign this excitation port, model wave port, change these to 4 modes. You will get in the new line just triangle to triangle. Now we are done with assigning the wave ports, and now we will have to assign the radiation box. Now we did look at how the radiation box should look at previously, and there we had defined that the padding should be 0 near the wave ports. Now what I will do to demonstrate is what happens if you by mistake forget to set the padding to 0. What I'll do is I will just create the open region as usual, operating frequency 10 gigahertz, and this is how a radiation box looks like in every other experiment apart from this one. And once you do this, let us just move on to whatever the next step is. The next step is analysis. We'll go to analysis or add solution setup advanced. The same thing as before, 10, and this, yep, not an issue. And one more thing I missed is the assignment of the materials. So you have box 1, which is the outer box, this will be copper. So for that, you right click on here, assign material. This is the metal, this is the actual metal of the waveguide, right? So you have copper. Now box 3 is the inside box, that will have to be air. That is the reason we put box 3 here in the first place. Air is done, and this vacuum is radiating surface, not an issue, done. We are done with everything. But what you will notice when you go to simulation and try to click validate is there is an error in the boundaries and excitations. Let us see what this error is. You can click on this error by going here. Yes, you can see exactly what I was describing. A wave port must have a solve inside objects on one side only. An internal wave port requires a PC object to be attached to and cover the opposite side before the solution can proceed. The cover the opposite side is the keyword here. That is what we have missed out on. And the cover by opposite side is done by just pushing this radiation box till the port. That will cover the other side of the wave port. And this is required for the simulation to proceed. So the way we do this is in radiating surface that we've given here, under the plus option, you have a create region option, which is similar to this to create box. So in the create region section, you will see a slightly different setting here. This is not the same as what we usually see, but what we have to get done is remove this Z padding. So you can see that in this direction, if you look at it from this side, you can see that this Z padding is what needs to be removed. So in create region, we will take the Z padding plus Z padding and minus Z padding, set it to 0. Done. Now the radiation box is also set, and when we go to validate, we will see that the 3D model and boundaries and excitations, everything is sorted. We will click analyze all and wait for the final results to come in. Now once the entire simulation is done, we can have a look at the results and see if we have got what we were looking for. So to do that, you can go into the results here. You have to right click on the results, and you will actually get two options: terminal solution data report and modal solution data report. Because we chose the modal wave or the modal wave port when we were assigning the wave port, then we will choose because of that we will choose the model solution data report. Here we'll go here, we'll click on rectangular plot, choose as parameter, and the plot that we need to see is S1411. This is the plot that we need to see. Clicking report, and this is what we will get. Now this is a slightly weird graph in normal contexts, but we do not need to be worried about it, because what is the most important is that this waveguide should be working at 10 gigahertz. And by the definition of working, we mean that the return loss at that particular frequency should be less than minus 10 dB. And we can see at 10 gigahertz, we have a whopping minus 70 dB return loss, which is very, very good for any system that we have to define. So this is a completely acceptable graph, and just because of the fact that at 10 gigahertz it is about minus 70 dB of return loss. Now in the lab exam, they can ask you to plot this graph on a graph sheet, so be prepared for that as well. Now this is done. This is the first result that you have to see. The second result that is remaining to see is the propagating modes. Let's have a look at the propagating modes, which can be looked at here. So what you do is you pick the air box over here, right click, plot fields E and mag E. What are we trying to do here? We are trying to plot the propagating modes, the modes in which the wave propagates within this structure. And the way we do that is by simulating what is known as mag E, which is magnitude of electric field. So you click this, click OK, and it will do some stuff. This is what we are wanting to look at. And this does not look very appetizing immediately, but what we can do to make it look interesting is in here under field overlays, under E field, this is the mag E one, which is what we have defined. Right click on this and click animate. What this does is animates the mode, and as you can see, there is a clear propagation here. So what you can do is you can increase the speed here to see the propagation move into this. Now this does not look very appealing, so one easy way to make it look better is, instead of going to mag E1, you right click on E field here. This is not a necessary step. I'm just letting you guys know, just in case you want to change the view. Here there's an option called modify attributes. If you right click on E field and not Maggie, you go here, scale, and you turn off dB. Now you can see a much more nicer looking plot. Same way you go to Maggie 1 and say animate, you will see how it is nicely propagating within the waveguide. Now this is the first mode. To see other modes, what you can do is in excitation, this is a compulsory step. You want to show all 4 modes to the examiner. You have to go to the excitations, right click and choose edit sources. So now what you can see here, you can see a lot of ports here, but it's actually simple to see. This is actually the first mode of the first source or the first port. This is the second mode of the first port, third mode of the first port, fourth mode of the first port. And over here, we have only excited the first mode of the first port. So to see the other modes, we'll have to turn this to 0 and turn this to 1. So now we will be able to see the second mode of this. Click apply, go to Maggie, you can see this as well. You can see how this is the second mode of propagation that we want to see. Similarly, you can also click animate and see it, but I won't be doing that here. Similarly, going back, excitations, edit sources, you can just change this to 0, change this to 1, and now we'll be looking at a third mode in the, and now you can see this is the third mode. And similarly, you will have a fourth mode. So you can go here, edit sources, make this 1, make this 0. That's your fourth mode. These are your 4 propagating modes within a rectangular waveguide. Obviously, the best one is the T10, the first one that we showed. And this is the end of this experiment. The results are showing exactly the way we want it to, and everything else is falling into place. This is the completion of the experiment for rectangular waveguides, which is more than half of all the experiments that can actually come. There will be 3 experiments out of 6 that can be rectangular waveguide. Hopefully this makes it a lot easier for you.